This is the first lesson of this course. First of all, I have to excuse me. Kimia, can you start your microphone down? So, okay. I have to excuse myself because I'm not an expert of the field, but since I played with computer since a long time, when pterodactyl still were flying in the in the sky, and so I remember when I entered the physics department, so the physics course, well, not the first, but in the third year, I was charged to do an experiment, and since tracing electrons in some field, so essentially measuring the ratio, charge, and mass of electrons. And so we took a photograph of this, and then we had to make the error analysis. And since it was a rather nonlinear system, the professor said, okay, you can use digitize in order to digitize the trajectory, and then hi Pierre, hi Paolo, and then you can use the Monte Carlo computation in order to estimate errors. You say, okay, and how? Using computers, and so I said, okay, and how can we use computer? Very simple. Here are the cards that are needed to compile the program. Here is the Fortran manual, and there is the punching, the machine for making holes, punching cards, and that's all. This was the crash course in computer that we had. Clearly, it was at the time an already old computer. Okay, and so I started to become interested in this. First of all, I would like to point you to some book which I found interesting. Last thing, since I was asked to produce a mock course, you mean massive open access course, because the University of Florence is planning to do. And since the format they choose imply a person speaking with very little animations, so essentially not suitable for physics, I thought to present this course as an example. So if something comes to your mind, something interesting that could be included in this history, please tell me so that I can say collect material and so on. So I would point you to some books. This is in Italian, but I think I have not. I tried to translate the slides in these last 2 hours because of Kimia, who is not speaking Italian. So sorry, some of them are still in Italian. But I think that you can find this also in English. Then, I have this is a very good book. This hidden language of computer hardware and software. This also is not bad. New history of modern computing. Most of these books are extremely boring because they speak of all kinds of, say, hardware and software, and a lot of them are more interested in the business field, so the economic aspects of computer evolution rather than technical one. While myself, since I'm physicist, I'm more interested in the technical details. This is clearly only Italian. It is a very nice report on a time we shall make this, I think, next lesson, when the time invented the personal computer and then threw everything away. And this is also an interesting tool if you want to build a computer really from scratch. You can start playing with this book, essentially. So it starts essentially not really building, but at least the concept, they start with the wires and then they build up all the computer. And this is another one, not really quite interesting. This is about deep learning, but I don't know if I am able to touch all the parts of deep learning at the end of the course. Okay, so in this first lesson, we shall only touch the first years of computing. And you have to keep in mind that computers are these people here. These are where the word computer was used, so in 100 years ago. So computer means someone who was able to perform a kind of computation. So if you see the Oxford English Dictionary of that time, one who computes, a calculator, a counter, and so. And this was one of the first, say, business enterprise of computers, essentially all done by hand. Here they already used, say, kind of mechanical machines, but essentially the organization also of modern computer inherits a lot of the organization of human computing. So why, you may ask, why you have to make a computation? Well, computation is quite old. This is a Babylonian clay tablet that reports a lot of, say, sides of Pythagorean triangles. You know, no, the easiest one is 3, 4, 5, but there are a lot of other triangles. And clearly, these are essentially quite interesting, because with a piece of a string, essentially, you can play with this. It is quite easy. You take a piece of string, then you divide it, say, in 3, 4, and 5 parts. So maybe it can be 3 meters, 4 meters, and then 5 meters. Then you join them as a circle. And if you keep them straight, picking it at 3, 4, and 5, you form a right triangle. So you can draw a very large right triangle, for instance, in a field, because maybe after some flood, all boundaries among fields were deleted. So you can track down and reconstruct right triangles using a string, essentially. And so since Pythagorean triplets is a complex problem to find them from scratch, because clearly you can, if you have a lot of place, you can use just one, 3, 4, 5, and that's enough. But suppose you have to build up a very, very long and straight triangle, because you have to measure something in a corner of a river. You need some Pythagorean triplet with, say, very weird ratio among sides. And so these are examples of first computational tables. And essentially, this is the beginning of computers, human computers, because since the time of Newton and then Euler and so on, they started to, science and mathematics become extremely important, and they had to find ways of making computation easy. And so it is quite easy to make sums, but multiplication is quite so difficult, because clearly, in principle, you can sum, and continue to sum two numbers until you find the multiplication of them. But this is extremely, extremely time-consuming. So, for instance, logarithm comes at handy here, because the multiplication of the logarithm of multiplication of the product of two numbers is just the sum of the logarithm of the two numbers. So, for instance, suppose you have to multiply 5,432 and 12,634 by among themselves. Clearly, you cannot make 5,000 sums. So you take this table here. You look for something that can approximate the logarithm of this. Since clearly you first, if you have 10 base 10 logarithm, you can divide or normalize them. So, for instance, divide by 10, so that you look for the logarithm of 5.43 instead of 1,000. Because I don't know if you ever used the logarithm tables. When I was in school, once they spoke about using this table, but then clearly everything disappeared with the handy calculators. But so essentially one time I tried to make this calculation, and also for preparing this page, and it can be done. So first of all, you have to scale the number so that you can find the number or approximation of this number on the table. So the logarithm of the 5.43 is 0.36 and so on. Then you scale this by 1, 2, 3, 4 places, and you find the logarithm of 1.26. Then you add them. Then you look in the table for finding the number C such that its logarithm is 0. Near to this one, and you find this one. Then you multiply by the factors that you removed, and so you find 69 million instead of 68 and something like this. Clearly, you can also interpolate the numbers, so you find the two neighboring one, you make an interpolation, and so you can refine further your results. Essentially, I think since the time, maybe also the ancient Babylonians, when they computed the forecasting of eclipses and so on, but in essentially from the 17th centuries, a lot of computation needed this kind of tables. Clearly, the logarithm and then trigonometric tables are a one-shot task. So once that you have computed everything, they are good. So you have just to check for errors and so on. But for instance, there are astronomical tables, which were very, very important for navigation. So the phases of the moon, the height of stars, and so on, were all elements that allowed to compute, to estimate the longitude of where you were. And remember that there is a very, very nice book called The Longitude by Sandra, I don't remember the name, but which is the history of longitude, which is an interesting problem because, first of all, since latitude is quite easy, you have just to measure the height of the sun at noon, and this gives you the latitude. But the longitude is a problem. Nowadays, we have solved this using clocks, essentially. So you have a clock which is set to the Greenwich time, and you see at 12, so at midday, you compute the local time. You compute the local time is 12. You see the difference between Greenwich time, and then you may estimate your longitude. But this was not possible before the invention of chronometer, and so they had to try to estimate where they were using astronomical tables. And if I remember well, once I read that the UK float, so they lose more ships due to wreckage because the bad estimate of longitude than in wars, for instance, against Spain and so on. So it was a really important problem. And so these kind of tables, or for instance, tidal tables, not to have the time of tide in order to enter some harbor and so on. So there was a continuous need of recomputing this table, and there were say an organization also, because for instance all of this number was given to two contractors and verified by a third one, and clearly errors were quite common. So in say at the end of the 18th century, Babbage, who was quite gifted in mathematics, started to be interested in automatic computation of something. Clearly, at that time, we are quite near the French Revolution. France was almost in bankrupt, and so they started thinking to increase taxes and to refine the census in order to be able to tax everybody with the right amount of taxes. And so they started to compile registry tables, and for doing that, they started to divide the task into a set of computers, human computers, clearly. The idea was that the great mathematicians like Legendre and Carnot were asked to set up the formulas, and then the human calculators to compute the digit following essentially an algorithm. So the idea of algorithm essentially arose for this kind of problem. So the idea of Babbage is that of applying this, say, factory principle from the Prony so inspiration, but try to automatize the computation using a mechanical device. This is one of the reconstruction of a piece of Babbage, the first Babbage engine, which was essentially a machine for making sums based on the Pascal system that we shall see in a few slides. But the problem here with mechanical devices is precision, because essentially there are, as we shall see, there are two approaches to computation. The first one is to use an analog approach. It means that you can use, say, essentially things that reproduce real numbers, and you can work on real numbers. But clearly, in that case, errors accumulate quite easily. On the other approach is to use a discrete version, so digitize things, and use, so essentially, Boolean algebra or some kind of algebra based on a finite number of symbols. So this is the difference engine. As you can imagine, it is an engine that makes the difference between two numbers in order to improve the interpolation of data. But at a certain point, while Babbage received the money from the UK government in order to refine this machine, he had the intuition that maybe one can also change the algorithm, not only the computation, but also the algorithm. And this was because in the Victorian times, there had been a lot of different improvement in the management of data. One of them was this clearing house, essentially because in London there were a lot of different banks, and each bank emitted its own cash, its own check. So at a certain point, you had checks emitted from bank A and received from bank B, and they wanted to exchange them. Clearly, bank A may have checks emitted from bank B. Bank B may have checks emitted from bank C, and so on. So instead of having all different so exchange of money and checks, they invented a system like this. Essentially, here there are clerks of each bank, and another clerk of each bank is going to the corresponding bank and clerk of the other bank in order to sign up the amount of checks and the money, so that one has to receive or to give. So at the end, instead of, say, transporting a large amount of money, you had only to balance the total, and so essentially almost no money was carried in the city. And finally, at the end, there was founded a Bank of England that was in charge of balancing everything. So at the end, you only had to increase or decrease the amount of your deposit in the Bank of England. So another important aspect that was essentially paving the way of modern connections is the telegraph. Here, the telegraph, first of all, it is a way of, say, digitizing an alphabet into a set of symbols. But at the beginning, it was just a point-to-point service, but soon one started thinking, okay, I have to send a telegram from London to Glasgow, but there is no direct line, so I can send a telegram to Manchester, and then Manchester to Liverpool, and then Liverpool to Edinburgh, and then Edinburgh to Glasgow, for instance, no? And so this is a kind of routing, but then you may say, okay, I don't want to take care of saying where this message should pass by, also because some lines can be out of order and so on. So the second service offered by the telegraph network was to find the right routing system, or the less expensive prices. Clearly, this is a private market, so everyone could charge the desired amount of money for passing a telegram. So also from the point of view of economics, one could find the fastest or the cheaper routing path between a given source and a given destination. And clearly also after sometimes also the idea of a hub arose, so that instead of sending a message, from all places in the UK, one can say, okay, I can send them to London, and then London is connected to everywhere, and so the routing is simpler. Okay, so let's move now to the United States. The United States was at the time a growing country. You see, in the 1840, say about 4 million people. in 80-60, 31 million, so 10 times in 20 years. And clearly, the census in the United States was extremely important because it was a democracy, differently from essentially all others countries, also including UK, which was it had a parliament, but the parliament was ruled not in a democratic way. In the United States, the number of deputies it corresponds to the number of electors. So they had to know how many electors were there and how they were distributed in order to allocate the number of, say, parliament places, essentially. And so, and also for taxes. And so it was established to have a regular census, and at the beginning, the census was done, say, at hand with people going and counting people. But all of it, I think, if I remember well, he was inspired by a fact that when you bought a ticket, train ticket, the employee was used to punch the card in order to make a description of the customer so that you cannot resell the ticket to another one. So, for instance, it had I don't remember if I have put it here. No, they had a hole for signaling the bear or not, another for, say, long hair or no hair, clear hair or dark hair, and so on. And so Herman Lorit had the idea of using punch the cards like this one, which are still, as soon as they existed, of the size of $1. And these cards had holes signaling numbers. Clearly, there are columns that say can specify the month, the year, the day, or the etc., all kind of things. And these cards are easily sorted by mechanical machine, also counted. For counting, clearly, it is just sufficient to have some contact, electrical contact, no, that makes a contact when you have a hole, so that it can count how many holes are in this row and so on. But also you can make a device where these cars were passing, and you can sort them or so divide them into bunches according to what was on. So essentially, you can see here the machine for making holes. This is a machine for reading cards. You see, you have a lot of contacts, so you put the cards on, and then you have these counters increased by 1 each time they count a hole in a given position. And clearly, this is a hand device, then you can automatize it. And so, when the United States rose to the number of 62 millions at the end of the 19th century, they only needed just 2.5 years to finish the census of the population. Clearly, it was a disillusion because they expected at least 75 million citizens, and so it was not quite appreciated. But another important point is related to office machine, in particular typewriters, which are mostly a successful introduction by United States Americans, because while Europe was quite organized in the sense of the office organization, but they essentially were not quite interested in having good, say, typewriter machines, because they have a lot of different, so people are able to write down quite clear. While in the United States, and this wasn't, probably they had no calligraphic school or very little, so they were extremely interested in having these new devices, and so typewriters. And there are some funny consequences. For instance, at the beginning, the arrangement of keys in the typewriter was in alphabetical order, and still we have a row of alphabetical order in the middle of the keyboard, F, G, H, J, K, L here, while the rest is essentially scrambled, because first of all, they noticed that two keys that were typed in too near succession, they tended to intervene the hammer. So they spread the letters that come frequently in combination into two opposite sides of the keyboard, and still we are our computer keyboard are essentially the same of these first typewriters. And finally, I think it is the third time I say finally, there is also the contribution of calculating machines, essentially sums. And the fact was not that of computing in reality, but that of recording things on a paper tape, because this was this avoided the need of keeping track and copying, making errors, all digits. So the idea was to have something that in some sense uses the technology of typewriter to have numbers printed on a paper type. And so you see now Burrow that for many times has also been a firm, a famous firm in computer industry. And the interesting part, which was then copied by IBM, was that not only they sold machines, but they started to build up the customer base, offering, say, discount prices and support service, so that it was noticed that it was much more important to have a network of customers than to sell a lot of machines by themselves. And another connected, related machine was, say, cash register machines. And and this is an important point that I forgot. The idea of building a loyal customer network essentially was invented by Singer, who was the firm that sold the sewing machines, and which was essentially extremely common. Almost every family had a sewing machine. And they developed the idea of having dedicated shops, so shops that only sold a kind of machines, and so on. So this was copied by IBM and also by National Cash Register, NCR, which at a certain time also became an important computer firm or industry. And now this is the famous Thomas Watson, who was to become the CEO of IBM, and he started as a seller, door-to-door seller of piano and organs, and then becomes to sell cash register machine. And they started also to develop techniques later used by IBM, like the idea of, say, bankrupt the the commerce of second-hand machines. So the idea is that I buy a cash register, then I buy a new version, and I sell the used one as a second-hand machine. In order to disrupt this business, he was charged to sell a new machine in loss in order to cut the possibility of making a business using used machine. And so clearly this was then punished by an antitrust law, but Watson and so Watson was fired. It was not charged, but he was fired because this was not no more an allowed method. Okay, and so the important the meeting point between these two, so the Hollerith and IBM was again the census problem, how to count and sort cards coming from the census in a quick way. And so this is one of the first IBM machine. Remember that for the most, I think most of the time that IBM has existed, so well before computers, they were selling machines for working with the punch the cards. So machines for counting, punch the cards, machine for sorting, punch a card, machine for separating, punching cards, and so on. All of them were essentially of this kind. So you put the punching card somewhere, then this is essentially the programming units. So I mean, here are the wires that say which holes has to be counted, for instance. Then I shall show you how this part was done. And this is where cards are recollected, and this is the counters of different holes. And but this was so essentially the programming of this kind of machine was done by rewiring a set of connectors. Clearly, you could you see that this can be removed, this part, because you don't rewire from scratch every time. The idea is that you remove the wire from altogether from the connectors, then you prepare another wiring device. You replace the wiring with the new one, and so, for instance, you can prepare. Clearly, it was a very time intensive problem to rewire. I don't know. There are about, I don't know, 1, 2, 3, 4, 5, 6, 7, 8 times 4, so 32 or maybe more holes. So you had to connect each of these to the related counters. So it was not an easy task. But you could remove this part, store it, and so use a new one. And so you had one wiring, say, for counting how many men are in the census, then another one for counting how many women or separating men from women, and so on. Okay, while this was essentially a single task approach to the computation, Babbage started, well before, started to consider the problem of chaining or concatenating a computation. No? So essentially, for instance, you could replace a multiplication by a set of sums. Clearly, making them by hand is a tedious way of making multiplication, but the machine can start summing and summing and summing and summing. And so he was inspired by these Jacquard looms. This is a Jacquard loom, in which the waving pattern to be waved on tissue was stored in punched cards. So essentially, each of these holes determine if a given wire was to be lifted up or left down. Then you lift a certain number of wires, then the loom is passing through all the looms of the wires that are in the upper position. Then you change the pattern, loom passes, and so finally you have a pattern appearing on the fabric. And so the analytic engine, this is a cartoon, but the idea is this one. It had a lot of, say, wheels that essentially were used for storage numbers, like in the difference engine. And you see here a lot of cards, essentially the same of the Jacquard loom, to perform a different kind of computation on this big storage. Clearly, everything was run by some engine, steam engine, and so on. And now, the interesting part was that clearly at the time it was extremely not clear what the need of this and so on. But in the 1840s, Babbage was invited in an exhibit in Turin by Vittorio Emanuele. You know, there are the period of the building of Italy, no? Essentially the movement, say, of fighting against Austrian in order to conquer the Lombardy and then Venice and so on. And Menabrea, who was to become prime minister, wrote a report, and this report was in Italian, was translated into English by Ada Lovelace, and who was the daughter of Byron, the poet. And she was able to have an intuition that one should try to translate an algorithm, so a sequence of operation, into elementary extraction, so that you can program this hypothetical machine. The machine was never constructed at the end, so Babbage was never able to find the funds and the mechanical precision in order to carry this project to the end. But Ada Lovelace was able to write down the first, say, essentially, program for such a machine. And actually, this was commemorated by a programming language, which is called the Ada, which is used somewhere. Okay, and you see here the schematized working of part of the differential engine. Essentially, they are all kind of mechanical wheels that essentially do what maybe I can show you the main idea. I'm pretty sure I had somewhere. The Pascal mechanical machinery that for sure I have in some slide is essentially a machine in which you have a set of wheels, and every time a wheel makes a turn, the next one advances by one. So essentially you can sum units, and then they accumulate into the multiply of 10, and then multiply of 100, and so on. And this essentially is the idea of Babbage. So if you want to play with all emulators of this and others, you can follow this link, the Formulab. I think I can show you maybe somewhere if I'm able to find the mouse. Formulab.ch. For me, is a French word for ants. So this is an ant lab, essentially, not Fermilab. And so let me see if I can stop the presentation for a moment. So this is the Formulab site, and you see a lot of different resources related to a lot of fields, but a lot about so old tools and so on, and there should be also the emulator somewhere of a Babbage analytical engine. Okay, so let me find again the presentation. Here it is. Okay, in the other side. Okay. And this is the Italian version. Let me find the English one. Window, this one, no. If I closed it. Oh, I'm not discard. File, open, recent history computer. Okay, this one. It was in another screen. And okay, so so the idea of the algorithm, I think you have quite so in mind what it means. But for instance, it is not so easy to communicate this idea to, for instance, young people. There are a lot of researches in how to communicate the idea of an algorithm. But for instance, you can take, for instance, to find the maximum common, I don't know the English name of divider, no, the common grand divider of two numbers. So essentially, you can, for instance, use a graphical representation like this, or you can define a kind of language. This is a kind of basic, essentially, and so specify elementary instructions to be followed until an end. And as you can notice here, the standard elements of an algorithm, but which were not standard at the time of Babbage, is the use of conditionals, if, and clearly of, say, jumps, go to. So the first, as I shall show you, these are rather modern to introduction in the field of computing, because the first usage of computation was essentially related to integrating differential equations. So the idea comes is back to Newton, essentially, and then Leibniz. The idea that you can define, first of all, you can define a function not by its equation, by as an algorithm in some sense, so a description based on a differential equation. And now, for instance, you can do the opposite. Normally, clearly, we are trained in the computational courses to have a differential equation and to try to find a closed form, for instance, a parabola, for the description of motion of something. But in general, it is as I shall show you, easier to compute a differential equation than to compute a functional expression. And so, since this is the most common task, because very rarely you can find the closest form of a differential equation, the original, a lot of original machines were designed in order to integrate differential equation. So here is just some crash course in differential equation, differential calculus that I think you are already at hand with, so I can skip this. But remember that the computation of a differential equation is extremely deeply related to the problem of computing integrals. So essentially, almost all numerical algorithm, or so analytical algorithm, in order to numerically compute the solution of differential equation, are the same used to compute the integral of some function. And okay, so these are examples. So for instance, if you have this differential equation with a given starting point x0 and given initial velocity v0, the integration of this is essentially the same as computing this function. And the same for elastic force. But for instance, consider this problem here. Now we are so accustomed to have functions in our computer that returns the cosine and the sinus of an angle, that, okay, for us, writing sinus of something is essentially no costly. But if you look at the algorithm, for instance, when I shall show you how the Olivetti programming machine was introduced, I have read the manual, and I tried also to write down a simulator for this machine. But for instance, the computation of a sinus was a program computer. You had to enter or record on a magnetic type the program just to compute the sinus of one angle. Clearly, on the other hand, this is extremely simple to integrate this differential equation. So, and you know that given a right starting point, you can have the sinus of the cosine or the cosinus of a given angle. So you take much less computer lines to integrate the differential equation than to compute, for instance, an arbitrary function. Okay, these are just the crash course in differential equations, which I can skip. And as I said at the beginning, when you want to compute something, you have two ways. First of all is to find an analog system that can be used to compute something. For instance, Galileo had this problem. He wanted to compute the area, for instance, of an ellipsis, because planets, Kepler's law, planets follow ellipses, and so, for instance, Galileo wanted to compute the area of an ellipsis. Clearly, now you have to decide how to compute this. The solution that Galileo found was to draw the ellipses on a piece of cardboard bounded by a rectangle, then to weight the rectangle, cut precisely the ellipses from the original rectangle, weight only the ellipses, and the ratio between the two weights gave the size, the area of the ellipses with respect to the area of the rectangle. So it was a kind of an analog computation. And another one could be, okay, since the solution of this elastic force is a sinus or cosinus, I can take a spring, let it start from some known initial condition, look at what the position is after a given time, and this gives the sinus of the desired angle. So these are computation. For instance, this is a kind of analog machines, you can see here, that simulates, it is essentially the integration of a Fourier development of the forecasted or measured tidal height. So essentially, you take a time series of the height of tides, say, I don't know where, maybe in the times delta. Then you make the Fourier analysis of this time series, and you find a series of sinus and cosinus. Then you can set up these wheels in order to, since the y and the x of these wheels gives you the sinus and the cosinus of the angles. So then you can resum with appropriate coefficients these sinus and cosinus, and so turning this wheel, you can have the production of, say, waves given by this Fourier analysis. So quite simple, but for us it is extremely trivial. But you can imagine that in the mid of the 19th century it was not trivial at all. And clearly the other possibility is that of reproducing your system scaled down. For instance, you can make a plaster reconstruction of some gulf, for instance, of the Zuider Sea, this one. Then you you start pouring water, and you see how the coastal pattern of a tide can, say, affect one or other polders here in the field. Now the idea really is to rescale things, and this is also what we usually do when we try to analyze it by hand, for instance, a differential equation. The classical first steps are that of adimensionalize, here there is an error, and so divide by the appropriate quantities, so that at the end you have a dimensionless equation that you can then integrate in a standard way. And for instance, this is one of the most used analog computers that was able to integrate, I don't remember, some 20 nonlinear means quadratic nonlinear, differential equations by turning wheels, essentially, you see here. And this was used also after the development of the first computers. And for instance, this is a very, very interesting device, also invented by Kelvin. So the idea is the following. You have to integrate a function. You have this thing here, this rod here is reproduces the function to be integrated. So essentially, you turn this wheel, this handle here, by r of t. So, for instance, you can make a turn to the right, and then after 1 second, a turn to the left, or half a turn to the left, and so on. And this moves these things up and down, so with a different radius with respect to the side, to the circle. Then the circle is running at a constant speed, and so if this is small, the cylinder here turns only by a small amount. No? So r, this r is the distance of these two balls, one which is in contact with the lower disc, and one which is in contact with the lower bolts and also with this cylinder. So if you move this part far, so large r, it means that given a turn of the lower wheel, it will turn a lot with this cylinder. If r is small, the same turn of the lower plate will cause a smaller rotation of the cylinder. So at the end, by moving left and right, these two, or turning right or left this wheel, you find the integration of any given function. Clearly, any given in the sense that you have to move these things according to this quantity. But essentially, this is an analog integrator. And one of the first industrial applications, only theoretical, was weather prediction, because starting, you see, in the 1818, the idea was that if you have enough data available and enough computing power, you could integrate essentially the Navier-Stokes equation and forecast the weather. And this was done experimentally at the beginning of the 19th century, the 20th century, by hand. So he, after 6 weeks of work, he was able to predict the weather 6 hours after the observations. And then clearly, if one man needs 6 weeks to make a 6-hour prediction, you have just to increase the number of computers, so human computers, and you can say have real-time predictions using only about 200 human computers. So the pattern was something like this. You need to have a physical representation of Earth. I mean, these are all offices full of people computing. The local computation needed for each of these patches. They receive by telegraph, say, the information from all the world where the measurements are done. They integrate the local part of the Navier-Stokes equation, and they represent the data on this feed. I don't know how was thought this, but so they physically have just to communicate with neighboring offices, and at the end you have a kind of director here who could ask, what are the weather prediction for here the coast of I don't know, Columbia, or something like this, or here the middle of say I don't know what is here. I think this is the Indian peninsula, this one. So essentially this was the idea. So a very industrial project made only by human computers to have a real-time forecasting. And actually this is the path that we followed. Now we have weather forecasting because we have, first of all, a lot of information from satellites, for instance, and a lot of computer power to integrate the equation of motion. If you are interested in analog computing, I once was in Pisa and there was a laboratory who was developing analog computers. Essentially, now clearly we have a lot of computer power, so that everything is made in digital. But either if you need a very, very fast response, for instance, in some particle detectors, or when so digital computers were expensive, essentially it was quite used to have analog computers. The basic idea is that of an operational circuit, which is essentially made by at least two transistors, and they are circuits that have an extremely high gain, so high that any small difference between the input is converted into a large, so essentially the saturation amount of voltage in the output. So if you feedback them with the signal, essentially with the negative feedback, the amplification is so high that you can consider these two points, since this is a grounded, so it is a zero potential. This also essentially go to a zero potential. So if this is essentially zero potential, but it can furnish current at will, then simply by comparing the voltage drop in these two branches here, you have that the gain of this feedback system is proportional to the ratio of these two resistances, so that essentially changing the resistances, you can multiply the voltage in input by the given factor. So if you, every time you have an equation and you want to make a multiplication for something, you do this. You put an operational with the two resistances, and here you have the signal multiplied by your factor. If now you put, instead of two resistances, a resistance and a capacitor, generally capacitors are used instead of inductance because they are more reliable. You can have both an integrator or a derivator of the signal. And so, for instance, clearly there is also a link where you can build up your signals. But for instance, suppose that you want to integrate this equation of motion, then you start by, so clearly you have to compute all resistances in order to have these numbers. So you can start by multiplying. Now this is just an inverter. You see the ratio is 1, so it is just an inverter. Then here you have I don't remember, but here you can compute. Okay, here you have one derivative. Here you have another derivative because of the capacitor here, and so essentially you compute all these factors multiplied by the right factors, and then when you the fascinating things of this circuit is that they are almost instantaneous. As soon as you switch your power on, you see the voltage, and this is the solution of the equation, the stationary solution of the equation. Okay, and so already in the middle of the 19th century, there were companies that sold computer power, so essentially computational power, in better. I mean, not by machine, but made by humans, or and all of them where, say, the storage was essentially standardized by punched cards. And so the just going faster, And this is a real fragment of the Babbage arithmetic machine that for some reason arrived in the United States, donated by, and here there is a clear in error, by the son of Babbage. And Aiken was enlightened by this, even though it has nothing to do with the Mark I, which was one of the first calculator. But he was able to convince the IBM to build up this kind of electromechanical calculator that, if you see, first of all, it read the instruction from a punch the tape, this one, which was essentially the idealization of a series of cards glued together. And it had no loop and conditional instruction. So if you have to repeat the computation 20 times, instead of writing as we do for I from 1 to 20, you took the computation and you glued together 20 times into the tape. And or clearly you can also glue the tape in a circular way, so having it run 20 times from the beginning to the end. And the speed of this machine was not, it was less than that of humans, trained human. You see here, now the tape glued together, but the important point was that it could work for days and days, essentially until the rupture of this paper tape, while clearly humans at a certain point becomes tired and start accumulating errors. So, but for instance, you can see here that for up to now, there was no idea that if then or do while loops were important. Why you can consider that Babbage and Lovelace already had the idea not of looping but of skipping. So if then skipping part of code when certain condition occurred. Okay, this is just an idea of computing an integral from an algorithm. And clearly, the Mark I was also the signal that computer business and scientists were not always hand to hand, because clearly the IBM wanted to have their own machines ready for a business world. So all well characterized by smooth and polished surfaces, and so on. While I can was not interested in this. And most important, when there was the first presentation, I can essentially did not mention the IBM contribution, who founded all the building. But so clearly it was the first divorce between the scientific and the business world. But anyhow, this was also used by von Neumann to carry on some calculation of the atomic bomb. And we are almost at the end of this first lesson, but we have to keep in mind that a very strong push towards the computation idea was the war. Clearly, the one of the problem that was also illustrated in the different the movie about the Enigma machine and the Turing was the game, the imitation game, was to how to solve the cryptographic system used by Germans in order to hide the messages from the Allies. And the idea, or the basic idea, is very simple: is the Caesar Codex, Now Caesar used to cipher his own messages simply using a disk of letters and other letters. So if they have 0 different phase, each letter corresponds to the same letter. If you shift the disk by, say, some position, so by one position, an A becomes a B becomes a C, and so on. This code is easy to be broken by simply frequency analysis, but what the Nazis did was to chain this coding, this cryptographic system using more wheels, so that at the end, and also some other switched tunnel, so that given a code that changed every day, they were able to code for messages. And the Turing approach was to build up this machine, the bomb, that essentially implemented a certain number of Enigma machines, because the same Enigma could both code and decode the message, and using some mathematical way of eliminating possibilities, and also the fact, at least what is mentioned in the movie, was that most of messages had the same beginning quotation, highly heated, and so a common part of the message is very handy for decoding messages. Also, what I've read is that the Secret Service of Alice used to pass information to Germans using fake spies in order to have the same message encoded by the Enigma, so that they could compare how a certain part of a message was coded. And so at the end, this bomb machine was essentially used to carry on brute force examination, so trial with different codes and different keys, and to see how one of these 36 Enigma machine was able to decrypt the given message. And during the Second World War, there had been a lot of need for computer or computational engines. First of all, the radar system, and also clearly the computation of a fire table, because essentially each time that a new weapon was developed, a new kind of cannon, a new kind of powder or propeller I don't remember the English name for the things that makes the bullet to be thrown. Now the explosive. So any kind that you introduce something new, you had to compute the firing table. I mean, integrating a differential equation given the resistance of air, so that you could aim at a certain target with the so not vanishing hope of firing nearby. And so essentially this was a school in order to prepare women, because at that time clearly men were employed in the war, so most of the computers were women. And in this school, the famous Moore School, they had one of these analogic differential analyzer that we have seen before, and they used to develop, using this differential analyzer or by hand, trajectories for each of the given inclination. You have also to keep in count Coriolis forces, so according to where you fire, you have different fire table. It is famous, for instance, that during, don't remember which war in the 19th century, in the Falkland, one of the Falkland War against, I think, Spain and UK, the British tables were not, so they used the tables developed for the northern hemisphere in the southern one. So they had, at first they fired completely out of the target, and then they had to change, to reverse all angles in order to fire in the good direction. And one of the big improvement, what time is it? I don't know if I'm speaking for too much time. It is
quasi le 4.
okay. Now I'm almost near the end. I hope. Let me see how many slides are here. Maybe we can stop at a certain point. Just to mention a thing that maybe you can not have noticed, but at the time of Edison, he noticed that at the time Edison was a supporter of DC current, not alternating current. So if you use DC current to feed a lamp, you notice that part of the lamp becomes darker than the other. And essentially, he, so at the end, realized that this was because clearly, since in some sense, the current is fed from one side to the other, there are part of the current which is positive, and part of the wire which is positive charged, and part of the wire which is negatively charged. Since for a given temperature you have emission of electrons, the electrons are charged negatively, and so they tend to go to the positive part, and they miss clearly the wire, and they finally impact on the glass, and so the glass becomes darker in the positive part of the lamp. Clearly, the idea, not immediate, was to put a grid, and essentially, I think I have the picture of one of the first, but these are one of the first vacuum tubes. Essentially, they are lamps with an additional, say, piece of wire. And so the idea is that if you have a filament that can emit electrons, and a field that accelerates to a cathode, and in the middle you put, so first of all, using just a filament and the cathode, you have a diode, because a current can only go from the filament to the cathode and not reverse, or vice versa, depending on the conventional sign. If you put a grid in the middle, you have a valve, so something that can let current pass or not according to the voltage of the grid. So essentially, you have a heater here that emits electrons, a cathode or another, depending on the sign. Maybe this is surely right. So you have an anode surrounding the filament and the grid. If the grid is negatively charged with respect to the cathode, nothing passes. If it is positively charged, the electrons emitted from the cathode can pass and reach the anode, so you have a current. And so if you use a high voltage difference between the cathode and the anode, normally these things work at a difference of some 100 volts between the cathode and the anode. Then with a small voltage in the grid, you can regulate a large current. And so essentially you have an amplifier. And I think I stop here. But this was the idea of building the first computers. So clearly you have, for the moment, you have just a valve, and then you have to find a way of converting a valve and maybe some diode into something that can store number, add number, and so on. And we shall see in the next lesson how this problem was solved by the first engineers who tried to implement algorithm using valves and so on. If I have put some link here so that if you want, I hope if it is working, I don't know, maybe I can. Okay, here is an interesting, I think, Veritasium. I have lost the window. Just let me see if I can recover now the save. No, I don't know where it is now. Window. Okay, maybe this one. And this, if it is no, 8 per 1000 non mi interessa, insomma. If it is the right link, it should be an interesting so animations on how first valves have been developed. Okay, a lot of publicity, and how this contributed to the first, say, computers and so on. So essentially, this is a step-to-step guide on how the very first circuit can be developed. So I think I'll upload the slides to the site together with the recording of this lesson. So maybe today or tomorrow you will have the lesson available. Oh, I think this is enough. If you have questions, I'm available. Otherwise, I can see you. Bye, and arrange for next Wednesday.
Io ho solo una organizzativa, come sempre è possibile trovarle online tutte, perché io ho problemi di concomitanza.
I shall. You can first of all have in teaching.complexworld.net. You can find last year recording in Italian, and I shall put the present one in English as soon as they are elaborated. Really, don't forget to record your presence to the course, either if you follow online or if you follow the recorded version of the slides, so that I can finally transmit the list of participants to the PhD office. Okay, so see you next Wednesday.
See you. Ciao ciao. Bye.
Recording.